maybe a lot of you know that there are many types of stars. Basically, the different types depend on the mass of the star. The greater the mass, the more brillante, or the higher the temperature of the star. So the more light the star is giving off, and the spectrum is shifted towards the visible and the ultraviolet. So there are stars very small, like these T-type stars or L-type stars. These make up a very few percent of the stars in the galaxy. And there are M-type stars, which are by far the most common stars in, at least in our galaxy. They make up about 76%. So these are red stars. So they're very difficult to see. Actually, we don't see them in the night sky. We see basically only maybe some very hot K-type stars and G-type stars, and these F, A, B, and O-type stars, which are the hottest stars. So we're really only seeing about, if we're lucky, maybe 10% of the stars in the night sky when we look up. So an important question then is, which type of star could harbor life as we know it, based on carbon? So our sun is a G-type star. So we know that G-type stars could harbor life. But what about these other stars? So when looking for a planet around one of these stars, we have to assume that our life is carbon-based and based on water, and that we will produce molecules similar, if not identical, to RNA and DNA. So we need, for example, a solvent, like liquid water. So that means that we need a planet which is revolving around each given star type at a particular distance.
Oh, espere, profesor. ¿Qué es harbor?
Harbor es decir, soportar.
Ah, ok.
Tipos de estrellas pudieran soportar la vida.
Ok, vale,
Okay.
gracias.
Claro, no en el estrella mismo, pero en los planetas que están revolviendo alrededor de la estrella. Okay. So we need liquid water, at least for life based on carbon as we know it. So that would mean for each given type of star, the planet which could harbor life, support life, would have to be at a different distance. Because if we had a planet like Earth at the same distance from an O star as it is from our G star, then we would have no oceans. Everything would have been evaporated, and most likely the water would have been split into hydrogen and oxygen, and the hydrogen escaped into space. So if we are to have life on this O-type star, it must be much farther away from the star, planet like Earth. And we'll see exactly how far away it should be in order to have liquid water on the surface. And in the other case, the other extreme is the M-type, or these stars, in which they give off very little light, and it's in the red. So in these stars, the planet would have to be much closer than the planet Earth is to the sun in order to have liquid water. So there are a number of conditions, not only on the star, but also on the location of the planet, and of course its atmosphere. As we will see, no, we need ultraviolet light, UVC light, on the surface, but not too much, because if we have too much and too short wavelength, it could ionize the molecules and thereby destroy them. And this question is important because we are about to allocate time on the James Webb Telescope to look for life or biosignatures of life on other planets of other stars. So we would like to know which are the stars that are more likely to harbor life like our own. Because of course, the biosignatures we will be looking for will be similar to the biosignatures that we find on Earth. So this is the James Webb Telescope that all of you know that it's being put up into space very successfully. And it's already taken some very nice pictures. So I think this is a real picture here. This is the difference between Hubble, the whole Hubble telescope, and the James Webb Telescope. The James Webb Telescope is really in the infrared. And the advantage of infrared is that it can travel through a greater amount of gas and dust in space without being absorbed. So, for example, in this nebula, this was taken with the Hubble telescope, we don't see the stars behind it. But with the James Webb Telescope, we'll be able to penetrate the gas and dust in this cloud of gas and dust and view the stars behind it. We can also go much further back in time because stars which are very far away from us are those which we are seeing in much earlier times. And they are very redshifted because of the expansion of the universe. So those galaxies which are very far away will be greater redshifted. In fact, they'll get to a point in which they are redshifted out of visible region of our universe. So we have what is known as the observable universe. Well, you all know that according to the general theory of relativity, that we cannot move through space faster than the speed of light. However, this doesn't apply to universes which are in expansion. And the velocities or the rates of separation of those galaxies due to the expansion. So there are, for instance, galaxies which are receding from us at faster than the speed of light. And those galaxies, of course, we're not going to be able to view. They're receding from us faster than the speed of light because of the expansion of the universe. Okay.
¿Otra vez podría explicar por qué se pueden alejar más rápido que la luz?
Okay, well, the theory of general or special relativity says that nothing can move faster in space than the speed of light. But the expansion of the universe is an expansion which is occurring at every point, and it's similar at every point, every place in the universe. So you can look at it as you have a dough, a bread. ¿Cómo se dice la masa? La masa, ¿no? Se dice en la masa. Tiene masa para pan en el horno y tienes pasas adentro. Okay, so you have some raisins within the bread and you heat the bread because you want to bake the bread, hacer el pan. Entonces la masa se expande. Y se puede dar cuenta que los galaxias, o perdón, en este caso los pasas, que están cerca uno al otro, están moviendo a menos velocidad que los pasas que están más lejos. Si hay una expansión uniforme del espacio. ¿Okay? Entonces, una de estas galaxias, la distancia es tan grande que la expansión del espacio se hace que la velocidad de retrocesión es más alto que la velocidad de luz. Entonces, jamás vamos a verlos. Entonces, lo que pudimos ver se llama el universo observable, the observable universe. Okay? But the point I want to make with the Webb telescope is that we can see farther back in time because we are looking in the infrared. So a lot of the galaxies which are exceeding from us are very close to the speed of light, but not greater than the speed of light, will be emitting in the infrared because of the redshift, because of the expansion of the universe. This is the Hubble effect, or the Hubble constant. But probably the most interesting for us, at least, is the detection of extrasolar planets with the James Webb Telescope. So they have in fact already detected about 4,000 to 5,000 planets revolving around different stars. Of course, most of them are in our own galaxy, while all of them are in our own galaxy. And most of the planets have been found around these what are called red dwarf stars. So these stars emit not so much light and in the red. So therefore, it's very easy to see a planet when it passes, when it transits over the face of the star, because we note that there's a big dip in the intensity of the light which is coming out during the time that the planet is between us and the star. Okay, in one of these red stars, for example, TRAPPIST-1 system, they've already detected, I think they've detected even more than this 7 planets here. They have detected even more planets around this TRAPPIST star. And they have also found on other stars planets, but it's much more difficult to detect. And why is that? Well, imagine this is the star. No, we have a red star and it's not emitting that much light. And we have a big planet which is close to the star. Then we could detect, for example, its atmosphere. So we could look for the absorption in the infrared due to the molecules in the atmosphere of the planet. And it's going to be much easier to do that on a dim red star than it's going to be on a big, let's say, G-type star like our sun or hotter star, in which it's going to be very difficult. If this is a planet, it's going to be very difficult to see a signal for the absorption spectrum for the molecules in the atmosphere of that planet. So therefore, most of the effort, which is going to be carried out with the James Webb Telescope, will be looking at planets on red-type stars. They're called M-type. These are M-type stars. But we will see that, in fact, these M-type stars have very little light in the ultraviolet where we need it to do the dissipative structuring of the fundamental molecules of life, if they are going to be like life as we know it on Earth. So it could be that they may be wasting a lot of their time looking at M-type stars rather than G-type and maybe even hotter stars or slightly colder stars. So we're going to do that calculation today and show the spectra of the different types of stars and show the probability of finding life on a given planet of a given star, given type of star. So basically then the reason that James Webb Telescope is going to be dedicated towards these M-type stars is that they're much easier to find, because you can imagine the light dimming of this star is going to be significant compared to the light dimming of this star with its planet system, which is much bigger and much brighter. So the relative difference will be very small. It would be very difficult to detect that in fact there is a planet, and even more difficult to detect the absorption in the infrared of biosignatures of molecules which could be on that planet, in the atmosphere of that planet. Another reason that they are suggesting or proposing to look at M-type stars is because, well, there's no ultraviolet light. So for them, ultraviolet light is very dangerous and could cause the destruction of life. So we know, for example, to get an ecosystem like Earth, we would need some kind of shielding from ultraviolet light. So they say, well, maybe better to start off with a star which doesn't have any ultraviolet light. But according to us, that star wouldn't be able to produce these initial pigments in the UVC, which are the DNA and the basis and the other fundamental molecules of life. So there are two perspectives here. One is the traditional perspective, in which the habitability is determined by low particle, because the stars also emit particles, okay? You know that we get hydrogen and we get helium and we get other particles leaving the surface of the sun and traveling through space at high velocities and causing the aurora borealis, for example, in our atmosphere. And they're also implanted in the moon rocks, for example, and some of the concentration profiles of these particles which are emitted by our sun have been determined by studying the penetration of these particles in the moon rocks. So these particles can also be dangerous for life because they can destroy, of course, the molecules. So they would like low particles giving off from the star, which would generally imply red-type stars or M-type stars, and little ultraviolet light, okay? Because they know that this ultraviolet light can cause damage even at the DNA level. For example, in this cyclopyrimidine dimers, they're called when you have two bases which are close to each other, for example, two thymines, then light in the UVC range, where we are interested in, can cause covalent bonding between the two bases and therefore destroy the possibility that the DNA can be replicated. Because once you have this covalent bonding between two adjacent bases, then the system can no longer be extended, replicated. So they would like low particles and low ultraviolet light. And the other criteria are liquid water, and that we have a magnetic shield on the planet. Okay, this liquid water on the planet, of course, and the magnetic shield. And the magnetic shield is basically to channel these particles, these high energy particles, from the sun or the star towards the poles, so that we don't erode the atmosphere, for instance. Like what apparently happened on Mars is that it lost its magnetic shield, and so much of the water that Mars could have had early on in its life had been destroyed by these particles and ultraviolet light, and the hydrogen left the surface of Mars, and therefore making it very dry world. Although they have found some frozen water on Mars now. So, well, really this approach to the habitability is really something rather ad hoc, at least with respect to ultraviolet. No? So saying low UV radiation, but it's not really based on any model they have for production, because they know that some of the molecules can also be produced by ultraviolet light. So ultraviolet light may not be so damaging or so bad for life, but they're not sure. So it's really an ad hoc approach. And our perspective through the thermodynamic dissipation theory of the origin of life is that we need some kind of thermodynamic viability. That is that we have non-equilibrium thermodynamic dissipative structuring. So that is the goal of life, is to dissipate. So the dissipation then is really what is fundamentally driving life. And for that, at least at the very beginning of life, we need ultraviolet light. And not only for the production, but also the proliferation and the molecular evolution of the system. So at the beginning of life, we are dissipating ultraviolet light. And so our criteria for finding life like our own on some other planet orbiting some other star is that we need liquid water again. Okay, we have this magnetic shield to avoid interaction of the particles with the atmosphere and destroy the atmosphere. But also that we need continuous UVC and UVB radiation on the surface. And also short wavelength UVC light in the upper atmosphere. And I'll explain why we need that. Basically to produce the precursors like hydrogen cyanide from other molecules like water and carbon dioxide. So we need that short ultraviolet light in the upper atmosphere, and I'll go into that in more detail in the following slides. And we need long wavelength ultraviolet UVC light on the surface. That's for the dissipative structure. So we've seen that DNA and most of the fundamental molecules absorb and dissipate around 260 nanometers, which is in the long wavelength UVC range. But we don't want any medium range, and that's, let's say, below about 180 nanometers on the surface, medium UVC light, because this can cause ionization of the molecule. That means giving off electrons and therefore destroying the bonding between the atoms. We also see that, well, we have seen already in previous classes that we need high surface temperature, particularly for the reactions which are leading up to these fundamental molecules. And well, with this surface temperature decreasing slowly in time, and a diurnal cycling of heating and cooling. That is to help us with the denaturing of DNA. But those are details. Maybe we'll talk a little bit about them later.
Oh, profesor, ¿y eso de tiene que tener este ciclo? ¿Hay algún como límite de tiempo? Ya ve que hay muchos planetas que, bueno, el día dura bastante o lo que sea.
Yeah,
¿Hay algo?
Yeah, that's a good question. That's a very good question. Those are details which we now have a model. I have this model which I have been working with Claudette. I'm not sure if she's here now, but we have this model for these photochemical reactions occurring at the origin of life in the Archean on Earth. And we can actually change the length of the day by just changing a parameter in the program and seeing what happens. We haven't done that yet. These are details which are still left to be, if anybody is interested in doing a thesis, no, we could certainly collaborate on that. There are many, many details that we can still look at. We are still trying to get enough support, let's say, for this theory that it makes sense to go into these details. No? So we're trying to look at the broader picture and trying to show the consistency of the model from the idea or the theory. And then once we have that, then we can go more and more into the details. But there are so many details that we just haven't had time yet to look at. So we don't know, Esmeralda, we don't know about the time of the cycling. It shouldn't really matter too much because, well, what the cycling for us does is the replication. So at the beginning of life on Earth in the Archean, a given cell replicated once a day. And remember also in the Archean that the days were shorter. At the origin of life, they were about 16 hours. The Earth was rotating more rapidly in the Archean. So we had 8 hours of sunshine and 8 hours of darkness at the equator. So we can play with this parameter and see how that affects the production rates of the different molecules. But we just haven't done that yet. It would be a very interesting. It may be that if we get too slow rotation, then some of the reactions get eaten up or get swamped by other chemical reactions. Some of the competing chemical reactions, for example, hydrolysis. And it could be that we, even after many, many days, but long days and nights, we don't have enough concentration to really to produce, let's say, a really evolved system. Okay, that's about all I can say right now.
Pues sí, está bien, Patrick. Muchas gracias.
Okay.
Sí.
Okay, so this now is our solar spectrum at Earth's surface through time. So the Archean at 3.85 thousand million years ago. Okay, that's the black line you see here. First of all, we had a less intense visible spectrum. And that's because, well, we know from sun through time analysis by looking at other stars, which are also G-type, but of different ages, we can determine the evolution of our sun. So it's pretty standard that at the beginning of life, 3.85 thousand million years ago, the intensity of our sun was about 30% less, basically because its surface area was about 30% less. So it had basically the same spectrum. The temperature of the surface hasn't changed much, but the intensity has changed. And we also know that we have this small ultraviolet peak in the UVC region. And how do we know that? Well, one of the best indicators is that all of the fundamental molecules basically absorb and dissipate very rapidly this light. So it wouldn't make